Radicals, square roots, and cube roots. So let's talk about some vocabulary with radicals. So the first thing is, what is a radical? Well, this guy right here, that little check mark, that's your radical sign. So your radical sign is that. Now, what tells you what kind of radical, if it's a square root or a cube root, is this little number out here. So this is called the index. So the index will tell you the kind of root, actually kind of radical you have. Whether it's a cube root or a square root or a fourth root, okay? Now, if there isn't an index, if it just looks like this, then that means the index is a 2, which we don't write it, we assume it's there, and that makes it a square root. So a no radical shown is a 2. Or sorry, no index shown is a 2. Now, this number on the inside, number of variables, whatever's on the inside, this is called the radicand. So the radicand is the expression under the radical. That's what the radicand is. It's the expression under the radical. So let's start simplifying. So the first thing we're going to do is we're going to simplify square roots. It's the first one we're going to look at. So square roots have an index of 2. These undo perfect squares. So for example, 4 is a perfect square. So the square root of 4 would be a 2. 9 is a perfect square. So the square root of 9 would be a 3. 25 is a perfect square. So the square root of 25 would be a 5. And you can continue this list. 49 is a perfect square. It's what times itself gives you this thing under the radical. So the first thing we're going to do is we're going to do the prime factorization tree. So that's breaking down 81 into what it's multiplied, all of its factors. So I know that 81 is 9 times 9. Now we're going to keep breaking this down until we end up with a bunch of prime numbers. So 9 can be broken down into 3 times 3, and I'm going to cross out the 9 because I broke it apart. This 9 is also 3 times 3. I'm going to cross out the 9 because it got broken apart. That's step 1. Step 2 is to group all the pairs. And we group pairs because it's a square root. That means we want to undo these perfect squares. So I see a pair of 3's here and a pair of 3's here. Step 3 is to box anything without a pair. Well, in this case, there is no number without a pair. These 9's don't count as either pairs or singles because these 9's broke down into other numbers, which we've already worked with. The fourth step is to pull the pairs out of the radical and keep the singles in. So right now, all of this is underneath that square root. So we're going to take the pairs out. So we have one pair of 3's that will come to the outside times another pair of 3's to the outside. So one number per pair. And guys, the reason why it's only a number, 3 times 3 is 9, and I know that the square root of 9 is 3. Same thing here. 3 times 3 is 9, and the square root of 9 is 3. Now, we keep whatever has no pairs inside. However, there are no pairs, or there are no singles. There's nothing left without a pair, so that means this square root will drop off. All we have then is just 3 times 3, which makes 9. And we already knew that. We knew that the square root of 81 was 9 because 81 is a perfect square. Okay? What happens if there's not perfect squares? So let's look down here at example number 3. Simplify, -3 square root of 48. So the first thing we're going to do is break this down. So 48 can be broken down lots of ways. The first way I come across is 6 times 8. 6 can be broken down into 3 times 2. 8 can be broken down into 2 times 4. 4 can be broken into 2 times 2. And I'm going to circle all my pairs. So here's a pair of 2's and a pair of 2's. Box in what's left without a pair. So basically, these here create perfect squares. 2 times 2 makes 4, and 4 is a perfect square. So what's going to happen is one of these 2's comes outside times another 2 outside times the square root of whatever's left without a pair, in this case, 3. So 3 is not a perfect square, so it cannot come out of the square root sign. But then we also have this -3 at the very front. So -3 at the very front will just multiply down to whatever the simplification of square root of 48 is. Now we're going to simplify the outside. So negative 3 times 2 is negative 6, times 2 makes negative 12, square roots of 3. So this is the simplified version of negative 3 times the square root of 48. These are the exact same number. It's just the negative 12 square root of 3 is a simpler version because the number underneath the square root is smaller. All right, let's look at cube roots. So cube roots are identified by an index of 3. So this little number here tells you that it's a cube root, which tells you you are undoing triples of numbers. You're getting rid of perfect cubes. So perfect cubes is something times itself 3 times, a little bit harder to recognize. The first cube root we have is actually 8. The cube root of 8 is equal to 2. The next perfect cube we have is 27, which is 3. 3 times 3 times 3 is 27. But the steps remain the same. We're going to do our prime factorization tree. So I know 125 is 5 times 25. I know that 25 can be broken down into 5 times 5. So once we have our prime factorization tree, we're going to group the triples because it's a cube root. So we want groups of 3. So 5 times 5 times 5 is a perfect cube. So 1 5 comes out to the side times the cube root of whatever's left without a pair. That's step 3. But again, there is no number without a group, so this cube root will just drop off and your answer is simply 5. So what that means is that the cube root of 125 is 5. It's a perfect cube because there's nothing left without a group. Let's look at number 4. So I know this is a cube root because of the index of 3. This is telling me to look for triples. And so we're going to break down 32. I can do 32 as 8 times 4. I know that 8 is 2 times 4. And I know that 4 is 2 times 2. So lots of things got broken down on that side. I can break 4 into another 2 times 2. So since it's a cube root, we're going to group in groups of 3. So 2, 2, and 2. Now I can't group these together because there's only 2 of them. I need 3 to create a group. So those 2's are going to have to stay inside your cube root. So we have the 4 from the very beginning. 4 times the single group of 2's that we can take out, the single group of 2's, times the cube root of this 2 must stay, times this 2 has to stay. And everything gets multiplied together. Now that we have everything in the correct place, we simplify. On the outside, 4 times 2 makes 8. Cube root of 2 times 2 on the inside makes 4. There is a square root of 4, but there is not a cube root of 4. Now let's look at operations with radicals. So you can do a few things. You can add them, you can multiply them, you can divide them. So with adding and subtracting, the key here is the radical and the radicand must be exactly the same in order to add the coefficients together. Kind of like 2x and 3x, you can add together to make 5x. Very similar, just like this. So that's example 5. Let's look here. So in example 5, we have the square root of 24 and the square root of 18. Well, right now, these are not like terms because their radicands are different, 24 and 18. So let's simplify these and see if maybe we have some like terms. So I want you to pause the video and I want you to use the process we talked about at the top of the notes and simplify the square root of 24 and simplify the square root of 18. Unpause the video and we will continue with how to subtract. And this is what you should have had for your simplification. 2 square root of 6 was the square root of 24. Square root of 18 simplified into 3 square roots of 2. So we were supposed to subtract these, but even after we simplified, we still ended up with 2 different radicands. So what that means is this is as simple as this expression is going to get because these are not like terms. You cannot add these together. Now let's talk about multiplying radicals together. So we have this rule here. If we have 2 radicals individually multiplied, you can actually multiply them underneath a single radical together. This is helpful if the individual radicals don't simplify, maybe the multiplication will. So if you look at example 6, it says simplify the square root of 3 times the square root of 6. So if we look at these square roots individually, 3 is prime, so that can't be simplified. And 6 is only 3 times 2, and neither of those give me a pair. So the individual radicals are not able to be simplified any further. But if I use that multiplication rule says that I can multiply 3 and 6 underneath the same square root sign. And now 3 times 6 makes 18. Well, the square root of 18 is something that I can simplify. I can break down 18 into 2 times 9. Then I can break down 9 into 3 times 3 and have a pair of 3's to take out of the square root, leaving only a 2 underneath. So using the multiplication rule is a way to help you simplify radicals that are multiplied together. Similarly, example 7 is the division version of the same rule. If you have two radicals individually divided, you can divide the radicands underneath one square root sign. And you can also go the other way around. If I have a fraction underneath that I'm not able to simplify, I can split that big square root into two smaller ones and divide them individually. That's helpful for things like number 7. So 8 over 25 is not something that I can simplify by breaking down. We're going to have to do something else. So instead, what we can do is we can use that division rule to make this the square root of 8 divided by the square root of 25. And then look at the denominator and the numerator individually. So I'm going to take square root of 8 and simplify. So I know 8 is 2 times 4, and 4 is 2 times 2. And I see that there are a pair of 2's here. So the square root of 8 actually simplifies to 2 square roots of 2. So the numerator is now simply 2 square root of 2. Over, now we look at the denominator and see if we can do anything with the square root of 25. Well, the square root of 25 is actually a perfect square. So the square root of 25 is equal to 5. So that's my new denominator. So this is as simplified as this radical can get. So what we've done is we've made it easier to simplify by splitting apart the fraction into two smaller radicals that are a little bit easier to deal with. We got a couple of examples at the bottom about adding and subtracting radicals. So I would like you to try example 9 by yourself. Please be careful to realize if you have cube roots or square roots to take out groups of 3 or pairs of 2 numbers. Pause the video, try example 9. First, you should have had for example 9. These are not able to be added because one is a square root and one is a cube root. Yes, their radicands are the same, but they don't have the same radical themselves. Pause the video, try number 8. And here's your solution for example 8. Now let's talk about one more rule. So when you have fractional exponents, what a fractional exponent is, it is simply a radical in disguise. So the exponent is built of an exponent and the index. So the numerator is actually the inside exponent on the base of a. So the base will stay the same, it's just instead of being rows into an exponent, it is underneath a radical. The denominator is actually the index of your radical. So that's how you change from an exponent form to a radical form. So if you have something with a fractional exponent, changing it to a radical is sometimes easier to simplify. So let's look at example number 5. If we simplify 90x squared y to the 7th all to the 1/2 power. So this here is the base. So what happens is to change this over, first we're going to write it in a square root, but the base is 90x squared y to the 7th. That's the base. So the numerator of your exponent is the exponent on the inside. So this is all raised to the first power on the inside. The denominator is your index. So there's a 2 out here on the side. So what we have is we really have the square root of, because there's a 2 here, the square root of 90x squared y to the 7th to the first power. Now, we don't need the index of a 2 because it's assumed to be there. And we also know that anything raised to the first power is just itself. So we can simplify this a little bit further by just having the square root of 90x squared y to the 7th. So we have changed this from being an exponential form with an exponent to a square root or a radical form. And this happens every time you have a 1/2. So exponents of 1/2, so 1/2 powers, those are just square roots. Anything raised to the 1/2 power is really asking you to take the square root. Well, now we ask, well, how do we simplify this? So we're going to pretend the variables aren't there for just a bit. Let's work with 90 just like we did all day. So 9 can be broken down into 3 times 3, and I can break down 10 into 2 times 5. So we want pairs of numbers because of the index of a 2. So we have a pair of 3s. However, there are variables over here. So x squared is really x times x. And y to the 7th is really 7 y's all multiplied together. And because you want pairs, we're still looking for pairs. So there's a pair of x's. And let's see, how many pairs can I make from the y's? I can make 3. And there's still 1 left over. So if we simplify this down, all the pairs will go outside the square root. So we have a 3 on the outside. We have an x on the outside. We have 1, 2, 3 pairs of y's. So 1, 2, 3 y's. Then the square root of whatever's left without a pair. In this case, 2, 5 times, and then the y. And then we simplify. So on the outside, 3 is just a 3. X, and then y times itself 3 times is y to the 3rd. Square root of 2 times 5 makes 10, and then the y stays inside. So this is the simplified version of example 5. Let's look at example 6. So example 6 is similar, except now we have a 3 on the bottom instead of a 2. So again, this here is the base. So what happens is we have the square root of 432, x to the 6th, y to the 3rd. And then now we have to deal with the fractional exponent. So the 1 is the exponent on the inside, and 3 is the index. So the 3 is here. So what we have is we have the cube root of this 432x to the 6th, y to the 3rd, all to the first power. So anything to the first power is just itself. So this is just 432x to the 6th, y to the 3rd. So similarly, anything to the 1/3 power is actually just a cube root in disguise. So 1/2 powers are square roots, 1/3 powers are cube roots. So what I'd like you to do is I'd like you to pause the video and try to simplify this cube root down. But remember, you want groups of 3 because it's a cube root and not a square root. And here's your solution for example number 6.